So we'll be calling it as, it is, if it is a conductor, and small n I'm calling as what? Number of free electrons per unit volume. Per unit volume. So small n represents the number of free electrons per unit volume, and the current will be written as AN EVD. This is a very important relation. A large number of questions have been asked based on this relation I equals to AN EVD. So we'll understand what is A here. So the area of cross section, this is area of cross section is A. E is the number of N is the number of electrons per unit volume. E is what? It is the charge of an electron. Charge of an electron. This is charge of an electron. And Vd here is drift velocity. Okay. So these are the parameters. So I is current, I is electric current. Okay. So you have to remember this formula. You have to remember this formula that I is your electric current, A is area of cross section, small n is number of electrons per unit volume, E is the charge of an electron, and Vd is drift velocity. Okay. So using this formula, a lot of questions have been asked, so you are going to remember this equation. Fine. And what is that drift velocity? So what happens when an external electric field is applied? Let's say I am making it positive and making it negative. So electric field is applied in this direction. So due to this external electric field, this electron starts experiencing a force in this direction, and when this electron starts moving in this direction, they will collide with each other. Okay, they will collide with each other, and when they collide with each other, then their path is not a straight line. They start moving in a zigzag manner. So they are not moving in straight line. They can move here and there. Then it will get collision with another charge particle. It will come down, and like this can move zigzag. So the path is not going to straight line. So in such situation, but ultimately it is going to be drifted toward the positive side slowly and gradually. So let's say this electron, if I'm talking about this electron, and it travels a length of x distance in t time, then drift velocity is written as x divided by t. So the electron has drifted by a distance of x in t time, then drift speed will be written as x by t, total distance traveled divided by time. So this is a very clear idea about the drift speed, that this is not the speed at which the electron is moving. This is the speed at which the electron is drifting in the conductor toward the positive terminal. Okay, this is the difference. So I hope you understood this one. And this drift speed is written as mu into E. This drift speed can be written as Vd equals to mu into E, where mu is what? Mobility of the charge particle. It is mobility of, in this case the charge particle is electron, so this is mobility of electron, and E is electric field. This is electric field. Okay. So E is electric field and mu is the mobility of electron. So this is one more formula that you have to remember, and based on this formula we'll solve few questions. Moving ahead, now I am going to define what is electric current. So electric current, how we define electric current? Suppose I am talking about this conductor, and let's say this area is, this is some area A, and there are some charge particles which are crossing through this area. I have taken the conductor of uniform cross section. Okay. So if I am saying through this area some dq charge is crossing in dt time. So in such situation, the current flowing through the conductor will be written as dq by dt. The current flowing through the conductor will be known as I equals to dq by dt, where dt is a time in which dq charge is crossing through this conductor. So in general, what we can say, the current is what? Current is defined as the amount of charge that is crossing through the conductor of a given area in time t. So in, let's say, some charge q is crossing through the conductor, cross section area of the conductor in time t, so we'll call the current to be q by t. So you can see here that if I have got the current I is dq by dt here, and the area of cross section is uniform, so everywhere whatever the charge is entering here at this cross section, that charge will cross through all the surface area. So everywhere the same amount of charge is crossing through any of the cross section of the conductor. So the value of the current will be same at all the point inside the conductor. So this is a very important point, that inside the conductor, if I'll see the current here and here, everywhere the value of the current have to be same, because whatever charges are entering here, the same amount of charge is crossing through this area, the same amount of charge is crossing through this area. So through all the area or through any of the cross section area of the conductor, the same charge is crossing, right? So everywhere the current is same. And you know that current is what? It is a scalar quantity. It is a scalar quantity. So it can be simply added or subtracted by using the simple rules of algebra, and no vector mathematics is required to add or subtract the current, okay? So let's say if one current is coming here and one current is coming here at the junction, and this is another wire, and the SI unit of current is ampere. So let's say 2 ampere current is coming here and 3 ampere current is coming here. So when I'll see the current in this, so I'm saying the current here will be the sum of these two current, and this is 5 ampere current, and this comes from Kirchhoff's current law that we will discuss in some time. But you can see there is no effect of direction. This 2 ampere current is coming here, 3 ampere current is coming through this wire. Both wires are having some angle, but that does not matter, because whatever charges is coming here, whatever charge is coming here, the entire charge have to flow through this conductor, okay? Because if this is higher potential, this is lower potential, the current will always move from higher potential to lower potential. You must have seen in this example that the charged particles inside the conductors were of negative type. These are the negatively charged particle, and they all are moving towards this positive side, okay? These all are moving toward the positive side. And the direction of current is taken such that direction of current is considered what? Is taken as that of the motion of the positive charge. Motion of positive charge. So in our situation, we do not have any positive charge that is moving inside the conductor, okay? We are having only negative charges that are moving inside the conductor. So the direction of current will be taken as the direction of motion of the positive charge. But as we have only negative charges inside the conductor, so we can consider the direction of current to be the opposite direction of the motion of the positive charge, okay? So we can see here that if electrons are moving in this direction, then we can think that virtually the positive charge is moving in this direction. And if this is the direction of motion of positive charge, so that you can see it is moving from higher potential to lower potential. So we have to remember one thing, that current always flows from higher potential. Current always flows from higher potential to lower potential. And if you have observed in physics, there are some more situation, like the heat energy, it always flows from higher temperature to lower temperature. The flow of water, it flows from higher pressure to lower pressure. So water, heat energy, current, they all flow from higher value to the lower value. In case of water, it is from higher pressure to lower pressure. Here it is higher potential to lower potential. In case of heat energy, the heat current flows from high temperature to low temperature. Okay, so the things are very similar, right, in physics. So current flows from higher potential to lower potential. This is one idea. So we have understood that current flows from higher potential to lower potential. It is defined as dq by dt. Direction of current is taken as the motion of the positive charge. Now let's say I'm saying that this is your conductor, okay, and for this given conductor, it's been given that that charge flowing through the cross section of the conductor at a given time t is given as a function of time, like it's given as 2t cube minus 3t square plus 6t plus 5. It's given like that. The charge flowing through the cross section of the conductor at any given time t is given as q equals to 2t cube minus 3t square plus 6t plus 5. And it's been asked that find the current, find the current through the conductor at, let's say, t equals to 2 seconds. So as the time is changing, the charge crossing through this conductor is also changing, because it is q is given as a function of time. So it has been asked to find out the current flowing through the conductor at t equals to 2 seconds. So we know that the current has been defined like this: I is equals to dq by dt, and we already have the equation of q, and it is depending on the value of t. So from here, if we have to find out the current, then we have to differentiate this equation with respect to time. So just differentiating this equation with respect to time, what I am getting is 6t square minus 6t plus 6, and 5 is a constant, and its derivative will become 0. So I have got the equation of current to be 6t square minus 6t plus 6. So just taking 6 common here, I'm getting what? T square minus t plus 1. I hope I have done the calculation correct. 6 I have taken common, then it is t square minus t plus 1. Now I want the current at t equals to 1, okay. So I will be putting t equals to 1 here. So this is 6 into t value is 1. So 1 square is 1 minus 1 plus 1. So this minus 1 plus 1 will get cancelled, and this will become 6 ampere. So the current value at t equals to 2 seconds is 6 ampere. If we will put t equals to 1 here, then what I am getting, sorry, I have calculated t equals to 1. Sorry, I have to calculate at t equals to 2. So I will be putting t equals to 2 here. So in this equation I will be putting t equals to 2, okay. So 2 square is 4 minus 2 plus 1, okay. So this 4 plus 1, 5 minus 2 is 3. 3 into 6 is 18. So this is 18 ampere. So you can see that the current at t equals to 1 second is 6 ampere, but the current at t equals to 2 second is 18 ampere. So the current is increasing, okay. The current is increasing. So this was one idea. They can ask the question in a different way also, like this. They can give you a question where they can say that the current passing through the conductor is changing with time like this 2t plus 3. They have given that the current passing through the conductor is given as I equals to 2t plus 3. Then they will ask you to find out the total charge passing through the conductor from t equals to 0 to t equals to 2 seconds, right? So the question can be find the total charge flown through any cross section of the conductor, from t equals to 0 to t equals to 2 seconds. Okay, so they've been asking that in a given conductor the current is 2t plus 3 and you have to find out the total charge flown through the cross section of the conductor from t equals to 0 to t equals to 2 seconds. So in this time period, what is the total amount of charge that has crossed through the conductor? That we have to find out. So I know that the current can be written as dq by dt. So I have written I as dq by dt from our definition, and this is 2t plus 3. From here we can say that dq equals to what? 2t plus 3, and this is into dt. Okay. Now we can see that this charge is a function of time, and this is in the differential form, and we know the value of dq here, right? And from here we have to find out q. So definitely we have to integrate this function, and we have to integrate within the proper limits. So the total charge flown is, let's say, capital Q, and here the limit will be for t. So it will be from 0 to 2. Just solving this integration, we can see that the charge is integral dq will be q, and we'll be putting the limit here 0 to capital Q, and that should be 2t plus 3 dt. Okay, so first term is 2t dt integration. The second term is integral 3 dt. Okay, and for both the integration the limit will be from 0 to 2. Now you can see that left side it becomes q, and here 2 will be outside because it's a constant. And what about integral t dt? It is t square by 2. So I'll be writing t square, and the limit will be from 0 to 2. Here 3 is a constant outside the integration. Integral dt is t, putting the limit that is from 0 to 2. So I'm getting here is this 2 and 2 will get cancelled. Putting t equals to 2 here, 2 square is 4. Then putting the lower limit, that is 0. And then this is 3. And this is 2 minus 0. So this becomes 4. And 3 into 2 is 6. And this is 10 coulomb. So you have seen that the total charge that has flown through the cross section of the conductor in this time period is 10 coulomb. So they can give you current as a function of time, and they can ask you to find out the charge flown through the conductor, or just in like the previous case, they can give you the charge as a function of time, and they can ask you to find out the current. So I've given you both the examples, right? I've given you both the examples. Now coming to the next part. The Ohm's law for conductor, right? And the current density, the concept of current density. Current density is generally represented by J. It's a vector quantity. So it is written as J vector. And how do you write down J? This is current per unit area. This is current per unit area. So J is equals to I by A, and if you want to write down in terms of vector form, so I is what? J multiplied by A, and in vector form it can be written as, that is J vector dot A vector. The current is written as the dot product of J and A, where J is current density vector and A is the area vector. So this can be written as, I can be written as J dot A. And what will be the unit, SI unit for this one? SI unit will be, this is ampere and this is meter square. So this is ampere upon meter square. So this is SI unit. The way you have to write down the current, that is J dot A, and like this you can find out. So let's say sometimes if we have to find out the total current passing through the conductor, where the value of J is not constant, okay, where the value of J is not constant. So in such scenario, we have to take an elemental area and we can find out the current through that elemental area, and we can then integrate it also, okay. Then we can also integrate it and then we can find out the total current. But that kind of problem are generally not asked in NEET exam. So just I'm giving you a brief idea about that. If sometimes the J is not constant, let's say the J value depends on a radius of the conductor, that for small r the value of current density is different, for another different radius it is different, like this. Let's say this is the cross section of the conductor and it's given that J varies, J is a function of r, okay. So as you take the distance from here, so for different distance the value of J is different. So if something is like given like this, that J is proportional to r, then if you take a small area here, if you are going to take a small area here, so here the value of J is different. So the current flowing through this cross section will be different. The value of J is different here. So if we are considering an area here, so the value of J is different here, okay. So the current flowing through this cross sectional area will also be different. So different current here, but if we'll add all the current, then we'll get the total current. So in those cases some integration will be required, but that is not required for NEET students. So I'm not discussing more on that. So just moving ahead. So if we see the Ohm's law at microscopic level, we'll find out the Ohm's law for a conductor, and that is J equals to sigma into E. So Ohm's law at microscopic level for a conductor will be J equals to sigma into E, where J, you know, this is current density, E is external electric field, okay, external electric field, and this is conductivity of the material, okay. So this is very subjective. Sigma is what? It depends on the given material, right? It depends on given material. So if we'll change the material, then obviously the conductivity will be different. Like for silver the conductivity is different, for copper the conductivity is different, for iron the conductivity is different. So for different material the value of conductivity will be different. And its value also depends on the temperature. Its value depends on temperature also. So as we change the temperature, the value of sigma will also change. So in case of conductor, what happens? In case of metallic conductors, when we increase the temperature, sigma will also decrease, okay? Inverse relation is there. Because as we increase the temperature, the speed of the electron increases, thermal speed of the electron increases with temperature, then more number of collisions will be there, and as more number of collisions will be there, then it will be difficult for an electron to move through the conductor toward the from positive terminal to the negative terminal. So it will be difficult for the charge to move across the conductor. So we'll say that the conductor is providing a resistance to the flow of the charged particle. And in such scenario, when by increasing the temperature, more number of collisions are happening, and it is opposing the flow of the charged particle. So in such scenario, the conductivity is going to decrease. So as we increase the temperature for metallic conductors, by increasing the temperature, the value of sigma is going to decrease. Okay, the resistivity will increase, but the conductivity is going to decrease. So if you increase the temperature for metallic conductor, sigma is going to decrease. So this is one property. So this is your idea for a given conductor. Okay, so if we are not changing the temperature for a given material, if you are not changing the temperature, then J upon E will be equals to sigma. Okay, so it is going to be a constant, right? So if we increase the electric field, the current density will also increase, so that the value of J and E, the ratio of J and A will remain constant, and it should be equals to sigma. So just write down and we'll move forward after that. And if you want to see it further, what is sigma at microscopic level? So this is Ne square tau by m. So N is number of electrons per unit volume, E is the charge of electron, tau is the relaxation time, and m is the mass of the charged particle. So sigma depends on the value of N, E, tau and m. So mass of electron is same for all the metals, right? So this relaxation time tau is same, N depends on the material. So you can see here, this sigma depends only on the material of the conductor and temperature. So sigma depends on N, number of electrons per unit volume. So for like copper, the number of free electrons per unit volume will be different. For iron it will be different. For silver, for gold it will be different. So sigma depends on N, and all other parameters E, tau and M are same for all the different conductors. Because electron is electron, whether it is an electron of copper or it is an electron of silver or it is an electron of gold. So all electrons will have same mass, same charge, same relaxation time will be there. So this E, tau and M factor are same. So sigma depends on N. So for a given conductor at constant temperature, J by E will be constant, it will be equals to sigma. So this is what I have to say in this topic. Moving ahead, and if we apply this concept to a conductor of uniform area of cross section, so let's say I am applying this to a conductor, we will see how we derive the Ohm's law that you know, because I know that you people know about the Ohm's law as V equals to IR, right? I know you don't remember this equation of Ohm's law for at microscopic level, but you do remember V equals to IR because you are studying this equation from class 10th onwards. V equals to IR. So I'll derive. You will say that, sir, your Ohm's law equation is different, sir. My equation is different. No, my equation, your equation is same. I'll derive it for you. So my equation is J equals to sigma E, and your equation is V equals to IR, but both are the same. I'll show you how it is. So if you'll see here, let's say this is your conductor, and let's say the potential here is V, and let's say the potential at this end is 0. this end is maintained at 0 volt. This end is maintained at V volt, okay. So you know, due to this, there some electric field will be there here, and that electric field will be written as potential difference divided by length. You can see the area of cross section is uniform, length of the conductor is L, so the potential difference divided by length. This is how I can write down E here. So E is equals to V by L. So the electric field which is being acting here is V by L. Now we know that J is equals to sigma into E. So J is current density, and I'm assuming that, let's say, some current I is flowing here, and let's say this area of cross section is A. So what I can write for J is I by A. Sigma is conductivity, and the reciprocal of conductivity is resistivity. So if I know that sigma is conductivity, then 1 upon sigma is what? It is rho. Rho is what? It is resistivity. It is resistivity. 1 by sigma equals to rho, and that is resistivity. So sigma can be written as 1 by rho multiplied by E, and E can be written as V by L. So you can see from here that rho L, I am taking this side, so this is rho L by A multiplied by I, and that is equals to V. Now you can see that for a given conductor, the resistivity is going to be constant, right? For a given conductor at constant temperature, sigma is constant. So if sigma is constant, then 1 upon sigma will also be constant, and that constant is written as rho, resistivity. So for a given conductor at constant temperature, rho, L and A, this everything is constant, and I am writing this as resistance of the conductor, and this is V equals to I into this rho L by A, I am writing with a constant, and that is the resistance of the conductor. So now you can see that your equation and my equation is matched. So this is the resistance of the conductor. So now you will be confused with something that's a resistance, R is resistance, rho is resistivity. What is the difference? So my dear student, you have to understand one thing, that R is the resistance of a conductor. Resistance of a conductor, and this value depends on the dimension of the conductor, rho L by A. So it depends on the length of the conductor, depends on the area of conductor. So for example, let's say you are having a square made of copper. You are having a square made of copper, okay? So this is made of copper, but it is having certain area. Let's say this is rectangle, right? So you have a rectangular plate which is made of, you are having a rectangular plate which is made of copper, and it is having length A and width B, but it is made of copper, so it will be having some resistance R, okay? This is going to have some resistance R. Let's say this is having R1. Now you have made a circular disc of copper. Again, it is made of copper. So now it is having some radius. The shape is also different. So is it going to have the same resistance? No, definitely not. Because resistance depends on length and area of cross section, right? So here, this disc will be having different resistance. Although both are made of copper, but their shapes are different. So this is having resistance R1, it will be having resistance R2. So shape will matter, right? All different shapes made of same material will also have different resistance. So if you have a wire which is made of copper, okay? It is made of copper. Its length is 1 meter, and its area of cross section is, let's say, A. Area of cross section A. Another wire is there. Its length is 2 meter. Area of cross section is A, and it is also made of copper. So will they have the same resistance? Definitely not. Because the length is changed, right? It is 1 meter, it is 2 meter, length is different. Material is same, area of cross section is same, but still length is not same, right? So R will not be same. So if it is having resistance R1, this will be having resistance R2. R1, R2 means two different resistance. If someone is having some value of resistance, the other is having some different value of resistance. So resistance will depend on the length and area of the conductor. But when I am talking about the resistivity, so I am talking about the rho. Rho only depends on the material and temperature, nothing else. It does not depend on the shape. Does not depend on the shape and size of the conductor. All the conductors made of the same material at same temperature will have the same resistivity. So when this resistivity and resistance will become same, so when R is equals to rho, and if I have made the value of L to be 1, A to be 1, so I have taken L equals to 1, A equals to 1, right? L is 1 meter and area is 1 meter square. In such scenario, R will be equal to rho. R and rho will become equal. So this is one situation when the resistance will be equals to R. So you can understand that the resistance of a material of specific length, specific area, specific length means the length of 1 meter, specific area means area of 1 meter square. So when you are considering the very unique, very specific dimension of the material, then its resistance will be equal to its resistivity. I hope this is clear. So this is the difference. Now based on this, they can ask you to find out different type of conditions. So let's understand one more point here. When I'm writing R equals to rho L by A, so what does it mean? So what is L here? L here represent the length of the conductor. Length of the conductor through which current flows. And what do you mean by A? Area of cross section from where the charges will flow, or area of cross section from where the current is flowing. Area of cross section, area of cross section from where current flows. So to make you even more clear on this, I am taking a specific example. Let's say I am having a cube or cuboid. Basically I am having a cuboid. So I am making a beautiful cuboid for you. So this should be appreciated, right? I am not good at drawing. I am very bad at drawing. So hopefully I have made a cuboid which looks like a cuboid. Thanks for that. So this length is, let's say, A, and this width is, let's say, B, okay, and let's say this height is C. And if I ask you that this particular surface and this particular surface, okay, if I ask you to find out the resistance between these two, right, resistance between this point A and this point B. So if I ask you to find out the resistance between A and B, it means that the current will enter from this phase and it will exit from this phase. So this current is moving like this, and for this you have to find out the resistance. So you can see that resistance is equals to rho, and the material is made of a material having the resistivity as rho. So this is rho, and then L. What length you are going to write down? as the current is moving in this direction, the current have to travel a length of A between these two faces. Between these two faces, the current is going to travel a length of A. So length I will be writing as A. Length I am going to write down A. And in the denominator, rho L by A, I have to write down area of cross section. So you can see the current is crossing through this cross section, right? So let's say this is E, F, G and H. The current enters from this cross section E, F, G, H, and I have to write down the area of this, because the current will enter from this surface and it will always go in this direction, and all these areas are equal, right? So I have to write down the area of E, F, G, H. So this length is B and this length is C. So area of this E, F, G, H will be what? It will be B into C. So this is going to be B into C. So the resistance between the point A and B is what? Rho A upon B into C. So this is the level of the clarity that you should have while remembering the formula and applying the logics. Okay. So today I have done till here, and then I am giving you few questions that you can solve. These are few questions that you can solve based on this. So that will be your homework for the session. And if you find any question to be difficult, then definitely you can ask that question in the comment box, and I'll be more than happy to give you the explanation to clarify your doubt. Till then, take care, bye bye, and prepare well. Exam is approaching. Don't get panic, just keep working hard. Thank you so much guys for listening me out. Bye bye.